Okay, so this is chapter 5, in which we're talking about data and business intelligence. So we've talked about this a little bit, earlier in the course where we had talked about this idea of the relationship between data and information. Data is collections of facts that can be processed into information, which they can be used for decision making. So this kind of relationship between data information, from a information technology side, this idea of business of BI, business intelligence, which is the process of taking data to information to make it usable for decision making. So the raw material we work with, in this process is, we start off with the transactional information, which is really what ERP systems do, what ERP systems do really well. So they generate, as they are executing transactions, uh, one of the byproducts of those transactions are different bits of data, you know, describing events or activities associated with the execution of that transaction. All right, so it's that becomes the raw material of which we then will take and then use to support, decide, create information that we can use to understand and direct our daily operational activities. So, the amount of transactions and the amount of transactional data that ERP systems that are generated, in operations is really substantial. So the idea of, for example, if you're looking at an example of like large scale operations, Walmart. Basically, Walmart generates 1 million customer transactions per hour. All right. If you look at Amazon, which is even more focused, since that's more of an online entity, generates something probably higher than that. So we're talking about pretty substantial amounts of data being generated on an ongoing basis that provides the uh, the raw material to work with. So this idea of analytical information is really the information that a manager needs to make a decision. So, like for example, what products are uh, what products are selling, what products are selling well, what products are selling badly. What is the anticipated, um, what is our workload at any given, our projected uh, customer arrival rate on particular days, like Saturday afternoon versus Sunday morning versus Tuesday at lunch. All these are different kinds of is information that can be derived from analyzing the transactions, the data that's generated from transactions. So the idea of the decisions to build a new store, or what are the implications of a like an event such as a storm, an incoming storm. What if you have that if you have that sort of question, it's like, okay, we have a storm coming in. What are the products that we should stock up on? I think actually, historically, I think analysis has shown that when you have a storm coming in, for some reason, people tend to store more, buy more Pop Tarts than they do ordinarily. So there's different things that can be um, facilitate decision making. As you're looking and evaluating situations. So this whole data information with the data being driven by ERP systems is a norm. So there's a concept as we look at this data and information. Is a question of what is the quality of the data. So really what we mean when we talk about the quality of the data. We're talking about the accuracy. Or the correctness of data. Uh, if, for example, as we will look here, if you look at a set of records, you can you can have holes in this. So, for example, um, you know, if a record, if a record is defined as having, last name, first name, street, city, state, all that key information, you could have in a record, maybe somebody did not put is missing a first name, or is missing a street, or you can have multiple records of a particular type, which you could say, for example, you'd have Jeff Jones, or you could have J Jones, or you could have J. Jones, or Jeffrey Jones. A whole number of different. You could have a Jeffrey Jones with a capital Jeffrey. You can have a Jeffrey with a lowercase j. All right. So you have all of these, all these potential, you know, abnormalities. I don't think I'm saying that right, but you have the idea. Variations. We'll use variations. Variations of data, which really make up the, we kind of can use to evaluate the quality of the data. So the ideal situation, you want to work with in making decisions and doing analysis. You really want to be able to work with high quality information, high quality data. The idea of taking information, taking data. So there's a process. A lot of times, what you'll do is you'll take data, which could be of indeterminate quality, and part of the transformation of moving it to information is to raise the quality of it. So the idea would be to go back and do evaluations and match, like for example, phone numbers and stuff, making sure there is a matching prefix area code on a phone number. And there's ways to do things like this. So there's a lot of tools that really can be brought to bear doing, involved with this data analysis process. Around that, what gets called, the term that gets used around this stuff is data cleansing. So, but the bottom line is that what you want to have is as accurate and as high quality and information as possible in order to facilitate decision making. Because obviously your decision making is only going to be as good as the data. If you have bad data, the odds of you making a bad decision is a likelihood. So the benefits of good information, really, the idea of as we say, improving the chances of making a good decision. So we've got a lot of effort. So the idea of being able to get to it's a good thing to have. It's really a desired situation. The challenge you run into, though, is that it doesn't happen automatically. As a matter of fact, data, the tendency is going to be for data to become, the quality of data will deteriorate over time if you're not watching it, if it's not being managed, if the quality of the data is not an objective and is not being managed. What will happen is that data will become, will gradually deteriorate over a period of time. So, an emphasis as we talk about, this idea of how do you get to good data, or how do you get to good information? It's a question of what we call governance. So the idea of basically putting rules in place, basically assigning ownership of the data, in associating standards with the data. Basically, what determines, really part of the challenge is to determine what is good data. So that's kind of a first, kind of your first step, and then establish, what are the rules, the guidelines, the processes that you want to be able to go through in order to maintain and sustain the quality of the data. So the term that gets used around this is called master data management, which is really a business process. It's a business function, business process. And a lot of organizations have actually made investments, have actually created groups in their organization. And these are not necessarily technology groups. One of the big things about data is there's always been this perception that data is a technology component. But really, the reality of data is it's a business component. So it requires business ownership, and the quality of the data is as a business function, ensuring that are business investments. So that's what this whole, the focus of being able to have good data that drives these, that you can put into your business, your business analytics processes, the fuel that makes the business analytics processes effective. The storage of data. So, part of it, so one trick is, there's really three elements as we look at data. One is to be able to generate it. The second part is to be able to store it. The third part is being able to use it. And so the generation of it is a function of systems. The applications that are automated with computer systems that are able to generate the data. The capturing of data is really, and to be able to use it, you need a structure. You need some sort of mechanism of a form that can be used to be able to hold and use the data. So what gets used, the technique, the tool, the platform that gets used for this in most modern businesses is what we call a relational database. So databases have been around starting from the 1960s. Right? So, it basically what databases are focused on, relational databases, is really came into play in probably the early 80s. That became the adopted platform. When really has, from the 80s, for about the past 30 plus years now, relational databases have been the standard for storage for enterprise applications and enterprise systems. So there's a concept of the relational database, which was a model that was defined by E.F. Codd back in the early 70s, that was built around this idea of relational algebra, which is a field of mathematics dealing with set theory. Codd translated that into really a set of rules that could be used for the storage and the creation, the maintenance, the management, and the querying of data. All right. This model became the foundation of what we call database management systems. All right. So there's a difference between a database, which is really a structure, and the rules of how the structure operates, and a database management system, which is a piece of software, actually a pretty big, sophisticated, expensive piece of software. Right? And what that does is it basically will let you, create, read, update, and delete data. There's different types of DBMSs. So for example, the ones that are probably most noteworthy that we see in most organizations is Oracle. They were kind of an early adopter of this. You've got other platforms like IBM has developed DB2, Microsoft has SQL Server. They are, those are different software platforms written by different companies. But the underlying, if you look at the way the database works, the relational database system, they all kind of work the same way. All right, so at the high level, what you have is a database, which is a database, which has has a basic common structure, of how it stores data. The individual database itself, which is really written in its own way, and then basically the user are using it. I think it's interesting is that you could actually store data. You can define a database in one SQL database system, and for the most part, be able to move it to another one. So, for example, like Microsoft Access, which is part of Microsoft Office, is a relational database system, which is designed just to run on a desktop. The structures, if you create a database in Access, that same structure can be transferred or moved over to an Oracle database or an SQL database. All right. So there are some, for the most part, there are some, some little differences and some, obviously some things that would have to be realigned. But for the most part, what we define in these, and the database models, the structure of the database models are the same. The databases themselves, the actual implementation, are different from platform to platform. So the structure of a database, there's certain things, COD defined that basically make up this relational model. So there's like 4 core components of how they structure data in a database, in a relational database. So the first is what we call a field, which is a single unit of data, which can be any individual attribute. So say, for example, say customer name or address or, or email or phone number. Those are individual types of data, or as we refer to them as a field, right? If you take a collection of fields, that then gets called out as a record. All right, so if you put, for example, first name, last name, address, phone number, date of birth, all of those individual fields or individual attributes combined together make up what we call a record, which is a row. So if we take like one customer, or your customer master record in Amazon would be the collection of all the different things which they use to, when you log on, to identify who you are, what you bought, things of that nature. That information is, there's multiple rows of data in a database. Each one, each row referring to one, being a collection of the data for one individual customer. We take that whole collection of all these records together. We come up with what we call a table. All right. A table is could be different sizes. So a table is made up of really both a combination of columns, or the fields, and records. All right, which are the rows. So if you think of this stuff as in the form of a table, it's a combination of both of the rows and the columns. All right, and from a size perspective, databases can hold millions and millions of records. All right, so there's nothing. They've actually, databases over the years, they've been optimized. A lot of work has been done around enabling the ability to store lots of larger and larger sets of data in a table. So I think on the width, the number of columns is usually something in the vicinity. I think the maximum is something like in the vicinity of like 200 plus or 300 plus columns. It depends. Database. It depends on each implementation. So Oracle will have a number of how many columns a table can have. Other databases may have more. Other databases may have less, depending. The number of rows is really a function, or the limitation number of rows is how much storage or how much data you can store. So if you have a large, you can put more and more disk storage, and you should be able to continue to expand a table, the number of rows in the table, to over at the levels of millions. Now that sounds impressive, but what's happened is, over the past couple of years, this idea of big data. Definition of big data is data has gotten so large you cannot effectively hold it in a relational table, or to be able to do all the things you want to do with a relational database. So you've seen this kind of a new generations of databases that are specifically designed around being able to store and access, rows of data, measured up into the billions. All right. So that's kind of your, and then the overall, if you take collections of tables, that's what we refer to as a database. All right. So basically you can have thousands of tables in the database, and the idea is each of the tables have a relationship to each other, which enables you to retrieve the data as per the rules of relational algebra. So the way you establish relationships between different tables, what you end up doing is you end up creating what you use a primary key, foreign key relationship. All right. So what a primary key is is a field or a field in a particular row or within a table for a record um, that makes it unique. One of the rules that Todd put out there in order to make relational databases work from his definition of it is a um, every table has to have one field that uniquely defines a each row. So we'll use a common example is a lot of times in database design, what you'll end up doing is creating one field and simply put a sequential number in there, which would make it unique. It would always be a 1, 2, 3, 4, 5, 6, 7. If you have a million rows, you can it's the next number. All right. So that is an entity that's an attribute that's in one table. How you connect two tables together is you take that same value and you will put that as an attribute in another table. So say for example you have two tables, all right, and you have one field in one. If you take that same field and put it into another table, you can then link these two tables together. So the example I always like to use is because everybody kind of knows what it is like orders from Amazon. So what will happen is, say you will have you come in, you put an order into Amazon, and it'll have a unique order number, it'll have a unique date and time of when the order was created. So that can be your primary key, the order number. You then buy a bunch of items. You can buy one item, you can buy 100 items. That's a repeat, and that could be a variable number. The way this gets represented is you have two tables. One is the primary table, the order table, which kind of has all the header information, and then and then in the I guess the item table, the item you're buying table, or the table that contains all of the items that you're purchasing. What you do is you put the order number in every row of that table. So you say, for example, you buy 10 items, there'll be 10 rows, and one of those fields will have the order number in it, which will then establish this logical relationship between the two tables, and then relational databases provide the ability to tie these two tables together and establish these relationships and be able to retrieve the data. You can find all of the data that all of the line items that were associated with that order across two tables. The idea of this is, once again, that the mathematical basis of relational algebra and relational theory requires that the rules that are established. So, say for example, the fact that every row has to be unique, and that you have to have a logical connection, two tables need to have a logical connection between them. Those are rules that have to be in place and be enforced, which requires a level of discipline. The good news is, if you follow this discipline and it works the way it's working, then when you run a query and you extract the data, when you get a query to retrieve data back out, you will get all of the data. You will get the result set that you bring back is correct. All right. So this idea of the advantages of a relational database, the reasons why relational databases play the role that they do in businesses. I mean, there's a lot of value associated with the ability to be able to store and manage and maintain data. So the idea is it provides the collective memory for business operations. It provides a place to put and access and analyze information, data driven, derived from activities in the organization. So these are some of the well-known advantages. Kind of well-defined advantages of using a relational database. So this idea of flexibility, scalability and performance, and being able to store large, relatively large sets of data. You know, information integrity. Remember we talked about data quality and and the correctness of data. Like, you know, the discipline that the rules of relational database apply allows you, you know, to be assured that when you retrieve data, it is correct, as opposed to, you know, bringing, you know, you bring data back and then you have to start evaluating whether or not, you know, what is the probability of this information being correct. The higher the probability of, you know, the better the quality of data, the, you know, the more straightforward, the more effective your decision making is going to be. And in addition, provides, you know, means by which you can establish and enforce information security. You know, one of the things that you discover, not everybody needs to see all of the data. As a matter of fact, there's a lot of cases. There's a lot of very sensitive information that's maintained in computer systems, and part of the functions of the DBMS, database management system, is it provides security that allows you to control and track activities dealing with that data, who's looking at the data, what they're doing with the data. And then the idea of also this reduced information redundance. You know, the discipline around this is such that, you know, you have to, when you create data, or as you're capturing data, as you're creating, you don't have to maintain it in multiple places, because if you maintain information and data in multiple locations, you start running into a question of, well, what is really the source of the truth? What is the correct, if there's 5 different results, or 5 different, you know, 5 different data repositories that have the same information, the question becomes, well, what's the real one? What's the correct one? So the idea of following the rules and the disciplines enforced by relational database theory, you can resolve that. You don't have to worry about you don't. There's less of a question of saying which one is the real one. From a models perspective, and where we see this, we see relational databases. Relational databases have been around for, you know, a fairly long period of time, but like 30 years plus. They were in place. You know, actually predate a lot of like the e-commerce stuff. So we saw the deployment of relational databases all through the 80s, and then in the 90s, as websites evolved and e-commerce evolved, we saw this sort of alignment between, you know, basically creating websites and being able to create dynamic websites that are populated with data from a relational database. All right, so, you know, if you look at the example we show here is Zappos, but, you know, any e-commerce site that you go to, any site, we'll have a construct. We'll have basically a front-ended by a web server, with the back end being a relational database. So the idea is you can run a query. You know, the web server will take, you know, the request, structure it into a query format, execute a query to find information, take the result set back, and then format it and present it up on the you know, for the consumer to see the results. So that, you know, this was kind of this has evolved over time, though. This is, you know, kind of started off, you know, the original websites, the original internet, or the World Wide Web as we know it, was really around static content delivery. All right, so what would happen would be, you know, Tim Berners-Lee's model was essentially for the sharing and collaboration of documents, around documents. So what would happen is you would put a request in, you would get a result back. All right, and that would be like a printed page or just static content. The merger or alignment of leveraging relational databases with web activity enables you to build dynamic content. You know, so you're not limited to just simply static pages. You're now able to create, you know, what we see now as these dynamic. And it helps enable it. There's other features that have come in with the web, but this relationship between websites and relational databases is a fundamental building block, you know, of e-commerce. Kind kind of another display of it. So obviously we have the web page, which provides the presentation. We have the database, which is the collection of data, which is which is the kind of the foundation of this. Behind this is the structure of the database, showing different tables and the relationship between different tables and how they can be connected together. And then this can actually, the information that we would derive from this can be taken and accessed by different types of tools. Like for one example would be if you have with a database being able to use a pivot table in a database. Not limited to that, there's actually a lot of different kinds of tools that are out there that can provide a wide range of different types of analytics against a database. So just another view of kind of what we deal with when we talk around e-commerce and the pieces of how websites relate back to relational databases. So some of the advantages we've seen, driving a website with data is, obviously getting the content of data. The content is keeping things organized and validated. Your content, so that when you bring things back up, it is correct. There's nothing worse than if you, say for example, if you're Amazon.com and that somebody puts a query in to find something, and every time you send a result back on a query, you would either add or subtract different things. I mean, so consistency, managing content is always a primary, is a primary requirement. The ability to deal with large amounts of data. So we're talking about, as we said, we're talking around the millions of rows of data, which is actually pretty, obviously it's not the billions when we talk around, with big data, but million is still a pretty large amount. Million of anything is a pretty large amount of data. And if you look at the size of e-commerce sites and kind of the amount of stuff they do, the ability to deal with this stuff and be able to deal with it efficiently and effectively is a big driver. And then finally, it enables you to standardize and simplify and take out the human element, the human errors, because obviously the more manually you deal with stuff, the more manual steps, the more human intervention of people changing and modifying stuff, you run the risk of introducing human errors. So the idea of simplifying, standardizing a process, and then automating the process in such a fashion that is repeatable, and consistently repeatable is really is really one of the advantages of what we're trying to do with this. Another piece of this data, of how you deal with data at from a business level, is this idea of a data warehouse. So a data warehouse is been around about maybe 20 plus years, and there was a lot of work done in the late 90s around kind of defining the parameters and the rules that we now associate with modern data warehouses. And what a data warehouse is really a specialized a specialized platform, as we call here, a logical collection of information from many different operational databases. It's a platform that is specifically designed around allowing you to collect data, to store data, to analyze data, in a consistent fashion. Where this really kind of came to play was when the original ERP systems were being put into place. ERP systems, and the relational database models that they're built upon are optimized for data, for basically creating transactions and storing of data on an ongoing basis. So the idea is, as you're generating you execute a transaction, all of the different pieces of data that are generated as we're kind of running through an end-to-end process, like for an order, creation of an order, the creation of a delivery, the generation of invoices, the payment of the invoices, all those records, all that information that's being generated. ERP systems do that very well, and they work very well with works very well with the relational model. However, being able to go back into that same structure, that same relational structure, and be able to do analysis of it, being able to correlate data, to be able to kind of identify patterns. Relational databases are not necessarily well designed for that. Right? So that's not their strength. And what happened was, over time, there was a need that was identified to be able to to develop a set of tools, a capability to be able to look up and analyze data. So the approach that was taken was, rather than continue to build upon the ERP relational model, basically data warehouses were designed with a whole different structure in mind that is specifically designed around, and we'll talk about that in a second, but a whole different model that is designed to optimally go through large collections of data and be able to do analysis. So the idea of a business data warehouse. You also hear the terms business warehouse. So that's some of these terms you'll hear different kinds of terms. The term we're using here is data warehouse, but you'll see you'll see basically this is a focus really to provide support for business analysis and decision making, specifically around not the creation of the data, but the analysis of the data, being able to look at it and make decisions. So, so as we look at this idea, it's a single repository, single data tool that really works in concert with the ERP system. So the ERP systems will generate data as part of ongoing activities. And then what will happen is we will take the information that's stored in the relational databases on the ERP system, and we will actually transform it. We will transfer it, extract it, transform it, and then load it into the relational database. So the term that gets used, you'll hear this term ETL, which stands for extract, transform, load, is this whole process. Well, it's a process and tools associated to facilitate the process of extracting data from different data sources. It can be one data source, it can be many data sources, it can be multiple data sources in an organization, or combinations of internal and external data sources. But it's the combination of all of these things are taken together and then loaded into a single repository, single data warehouse, which can then be processed to do analytical work against that data. So the model, as we look at this stuff, if you to compare a data warehouse to, say, a relational model used in ERP, relational database, they're all represented by two-dimensional tables, rows and columns. All right, so it's relatively flat. And what we do is we have relationships. We define the relationships between multiple tables and combine things together. And a data warehouse, information is what we say multi-dimensional. All right, so there's different combinations. There'll be different layers of structured in a different way, actually in the form of a cube. All right, so the term that gets used, you'll hear this term data cubes, which is actually a whole different way of storing data than a relational database. All right. So, to use an example here, probably the best way to illustrate it is maybe just kind of showing a picture. So this would represent what we see here is a representation of an example cube that would be from maybe a Walmart or an Amazon. All right. What you see is three, and the cube is obviously 3 dimensions to a cube. All right, and so in the case we have here is we've taken a whole bunch of transactional data, all this transactional data we've taken, and we've gone back and we've taken all that data and we've reorganized it across 3 dimensions. All right, so we've got stores, so we have products, we have stores, and then we have what we call promotions, which is, different. We're going to sell something at a certain price with a certain advertising for a certain period of time. All right, so so what we do is we organize the tape, we organize the data, aligned by stores, and then within each store, products, and then for each product we have a promotion. All right. So so we would look at this. The overall cube is kind of the relationship combination: all stores, all products, all promotions. All right. But what we have the ability to do, though, is we can kind of slice and dice this cube. If I want to find a particular, slice of information or piece of this overall structure of data, for example, I want to know, across all stores, across all products, how we did with promotion 2. I don't care about promotion 1s, 3, and 4 for right now. I want to know how we did with promotion 2 across all these different dimensions. I can very easily pull that information out. I can easily extract that information out. All right. I could also, but by the same token, if I want to go back and say, gee, I don't really care, what I want to do is I want to drill into this more. I want to know from promotion 3, I want to know about all stores, but I want to know about product B. So I want to, or maybe A and B. I can pull that out as well. All right, so I can drill this thing. So it becomes very effective. So by pre-organizing this data, the effectiveness of the analysis can be, optimized. As opposed to if this data was stored, say, in a relational form, you could do the same analysis, but it would require a lot more work of gathering information and kind of organizing it and structuring it to be able to get to the point where you could find it. So it's not a matter you couldn't do it; it's a matter of the efficiency, and especially as we get larger and larger and larger data sets. So as we start talking about millions and millions of rows of data, and trying to do this stuff in an efficient, effective fashion. All right, so that's kind of what this idea of the cube is. And the cube is, as I said, the cube is the techniques and the methodologies that are associated with data warehousing have been around a while now. So, they were kind of developed in the late 90s and have really been kind of established as kind of industry standards, and has been baked into a whole series of products. So this is the underlying structure and that gets used by analytics tools. So you'll see like data warehouses and analytic tools that are designed to kind of create all the stuff and have you work with it. Once again, we talk around data quality. One of the big things, a big piece of this ETL process, as we're taking data from these different, it could be from one transactional system, it could be from multiple transactional systems, it could be from external sources, or any combination thereof. One of the challenges is to do information cleansing and scrubbing. All right. So, like for example, would there be somebody could have a whole bunch of records out there from some source for some reason. They would have had a date of February 31st, 2010. Well, that's probably not real stuff. So part of this ETL process, and it's baked in a lot of the tools and capabilities to be able to do this stuff, is as you're going through this transformation and loading process, you're also cleaning data. You're also identifying and aligning and adjusting. Because really what you want to do is you want to keep as much, you want to load as much accurate data as possible, because the more incorrect data or misaligned data or data with abnormalities in it basically affect the quality of your output or your quality of your analysis. So the cleaner is better. So the trends we've seen, has been with data. So this, as I said, it used to be 1 million rows was a lot of data. 1 million rows is not as much data, or is not considered as much data anymore. All right. So what we've been seeing is larger and larger amounts of data, larger and larger data sets. So what drives a lot of this stuff, for example, is this idea of consumers, being enabled using smartphones, being the rise of social networks, the ability to generate of these powerful handheld devices that have the ability to generate, amazing amounts of information and being able to capture it and be able to store it for future use. So what we've seen is, more and more the ability to put more and more data, capture, store, and process larger and larger amounts of data. So what we call, so there's a lot of techniques, there's a lot of stuff that's been out there that it's, has been established and continues, and quite frankly, continues to evolve as the data sets and the amount of data we can process get larger and larger and larger. The different data mining techniques to be able to go through, very large sets of data to be able to identify trends and patterns and correlations and all of that, all of those types of things are really it's kind of the norm now. All right. So the other thing we've seen, kind of this driving of big data is, we've had historically when we look around relational databases, we would call that structured data, obviously in a relational database with rules defining, all, basically defining what is the content of the data, what's defined, what do things mean. That's all part and parcel of what we refer to as structured data. All right. However, as we've moved ahead, we're seeing more and more unstructured data. So as we look at things like, for example, social networks, people are, entering, people are just typing, like their own, like sentences and paragraphs, which is data, and there's a lot of stuff within it, a lot of potential information to derive from it. But there's not a structure. A relational database, a two-page blog is different than a 2,000 row relational database, even though they might refer to the exact same thing. All right. So this idea of the data, the sources of big data, a lot of stuff is actually in the unstructured fashion. One of the challenges being able to take unstructured information and then be able to kind of analyze it, and provide the types of definitions and alignments that we see that are baked into the structured model. So that's a lot of what we're seeing now. So this becomes, so the growth we see is in unstructured. Though, we still see growth in structure, but the real growth, when we talk about this explosion of data, of big data, how we get to big data, a lot of it is unstructured. So part of the challenge is being able to deal and cope with that. And then ultimately the goals and objectives of what you want to be able to do is take all of these large data sets, unstructured and structured, and analyze them, and then be able to display, be able to present it, be able to communicate it, in a fashion that people can easily understand. And the way people, the one technique that really is you're very successful with is this idea of using visualization. Being able to draw, pretty pictures, but it can tell a story. A well-designed visualization can tell a story more effectively than maybe 5,000 words or more. All right. So that's kind of what we're seeing. So this big data, once again, big data is defined as data so large, normal relational database models have difficulty working with it. All right. And then we're seeing, but this has been the trend for the past couple of years. This has been the engine that has been driving organizations, and pretty much this is, we are still probably in the upcycle of this. We're still growing, we're still looking and still expanding in this domain. So, and that is about it for chapter 5.